Okay, hello everybody. Nice to see you all. Thanks for coming. I'm going to be talking about discardable in-memory materialized query, which is a very long phrase, but I'll explain what it is later. First of all, I want to introduce myself and tell you a bit about my background. I'm an architect at Hortonworks. I've been there since September, but I've been working on some of this technology for longer than that as open source projects. I've been working in open source for a long time. Most recently, the project I work on most of all these days is Apache Optic. It's just been it's a query optimization framework. It's just been accepted into Apache Incubator, and it's being used in Hive and Drill and cascading. I founded Pentaho Mondrian a few years ago, which is an open source OLAP engine or an in-memory analysis engine, and that's part of the Pentaho suite. I'm still involved in that project, although not as active as I was. But Mondrian has kind of driven some of the, I've been a user of databases and data management systems as being an author of Mondrian. So this has been driving some of the things that some of the directions I've wanted to take Hadoop in. I'm a committer in Drill and Hive. And in the past, I've been at various database companies. I'm basically a database guy. I was chief architect of SQL Stream, which does streaming SQL, similar to Storm, but with a SQL standard interface to it. I was chief architect of Broadbase, which was one of the early Windows NT-based data marts. And then before that, I was at Oracle. So as you can see, I'm an open source guy and a database guy. Some disclaimers. So this isn't a product pitch, and this isn't even about an open source project which is available to use. This is a summit, and what I want to do is start a dialogue about how we should be solving what I see as some of the challenges that Hadoop has, so we can get it a little bit closer to perfect. Yeah, this isn't complete software by any means, and there are some architectural ideas here, some work has started, but I want to start a discussion. I'm a database guy. I initially looked at Hadoop skeptically, and then I was won over by its just ability to scale, its openness, and the community aspect of it, and I basically saw that it was going to become the next generation data management system. And I kind of made it my mission to look at the good things about databases. Initially Hadoop threw out all of the good stuff about databases, like metadata and so forth, and query optimization, and a lot of those things, and security. And a lot of those things are coming back into Hadoop. So it's kind of my mission to try and speak both languages and bring in what database technology, the database approach that can help solve some of the problems that Hadoop has. And since a lot of people that are using Hadoop are accustomed to using databases, it makes Hadoop easier to use if it looks more like a database. But at the same time, let's preserve the some of the stuff that makes Hadoop wonderful and different than DBMSs. So one of the criticisms of Hadoop today is it is brute force, right? It allows you to muster a huge amount of disk space and compute power and memory, and it can achieve some amazing things because of that brute force. And then recent projects like TAS vectorization are making Hadoop better and stronger. But the application kind of has to know how to use that brute force. And certainly until there was sophisticated query optimization, it really was down to you to channel that brute force in a good direction. I'm a big fan of business intelligence. I've been involved in this as part of the Mondrian project, And the best practice is still, for interactive analysis, the best practice is still to take the data out of Hadoop and into some in-memory analysis platform. And why I see why that makes sense today, I don't see why it is fundamentally necessary. So I want to see how much we can do using the resources inside Hadoop. So I want to make Hadoop smarter. And so where I see us at right now is, brute force, like the mustered forces of the US military can achieve an awful lot, but a little bit of diplomacy, a little bit of intelligence, and how you use that force can make it a lot more powerful. Let's look at hardware trends. These are driving the same thing. We've gone in the last 5 years, and this is a typical server configuration. My friends who work in big web properties tell me this is the typical configuration, a Hadoop cluster. Number of cores has gone up, the amount of memory has gone up, but we're not seeing memory and disk are still staying fairly balanced. There's a lot more memory and there's a lot more disk. So for the foreseeable future, I mean, maybe solid state disk is going to become cheap enough that people will stop having spinning disk, maybe. But I think we're still going to see a heterogeneous mix of different storage types. Hadoop has to function across all of those storage types if it's to be cost effective and if it's going to be performant. So what to do about memory? We haven't really come up with a good solution yet. So here's one dumb way to use memory. This is how Hadoop mainly uses memory today. Buffer cache. That is, keeping copies of disks, of blocks you've read from disk, keep the copies in memory. We take a simple example where you've got, you can multiply these numbers by a factor, it still works out the same way. If you're doing a scan of a table and you have, 50 times more data on disk than you have in memory, by the time you get to the end of that scan, you've blown away all your cache, and what exists in memory is the last 2% of the data on disk, and then you start that full table scan and you don't get any advantage from your memory. So you might as well not bother in that particular case. If that's your pattern of access, and a lot of data that's accessed from Hadoop is scanning all of the records. If that's your pattern of access, your memory really isn't doing you any good. So let's try and find a better way. This is analogous to virtual memory. If you have, let's say you've got a machine, a laptop with 8 gig of memory, and you decide to give it, 80 gig of virtual memory, then if you decide to fill up that 80 gig of virtual memory, you're going to spend an awful lot of time paging. You're not making good use of that, even of that 8 gig of memory that you've got. So, don't kid yourself. You have this huge address space, of which a small proportion of it is memory. Another dumb use of memory, actually it's not so dumb, but I call it document-oriented analysis. It's actually really, really great for some kinds of work, like machine learning, where you can work on I'd call it a medium-sized amount of data that fits in memory. And this is not just the memory on one node, this is the memory on your entire cluster. That's still a lot of memory. If you can do that, then yeah, you want to load that particular set of data into memory and work on it. But machine learning algorithms often work well like this. But if your problem grows, it's larger than memory, then you're out of luck, and the algorithm just kind of crashes. The performance crashes. So a smarter use of, this is kind of a, materialized queries are, in my view, a smarter use of memory. And the basic idea is that rather than going back to the raw data set all the time, go back to an intermediate result, a summary of the data that is in memory. And don't require your application to be smart enough to find that summary, but make the system, the query optimizer or whatever is doing that role, smart enough to transparently redirect your application to the materialized query. And it also helps if that data is in memory, which is easier to do because it's often a lot smaller than the raw data, then it'll go a lot faster. Let's have a kind of more concrete example of this. Just imagine there's 300 million people in the US, plus or minus, and so imagine you have a census table with 1 record per person in the US. And this, you know, and the question, you want to ask a question like, how many people are there? Which is, you know, select count star from census, or which state has the most males. Any of those questions, you're probably going to have to read the entire 300 million records. And so it's going to take, well, if you've got a Hadoop cluster with 1,000 nodes, it isn't probably going to take very long, but it still takes a lot of brute force. And it's a dumb thing to do, because if you're going to ask a lot of questions about individual states, you know that it just makes sense to use summaries. So it's smarter to create a census summary table that has 1 record per state and gender. That's 100 records total. And you can answer that query that, you know, is drawing on 300 million records. You can answer that query by reading 50 records. And that table uses a minuscule amount of memory. It makes an awful lot of sense. And the census data doesn't change. It only changes every 10 years. So it makes a lot of sense to keep that in memory. Databases have had a thing called materialized views for a very long time. I think, you know, mid-90s are when they started rolling out, coming out of research and into production products like Oracle and DB2 and so forth. The idea of a materialized view is that it is a table and it's a SQL statement, which the table is equivalent to. So the system knows, here's this data, you know, 1 million records or whatever it is, and here's the query that populated it. And when you execute a query, the optimizer goes, aha, he's asked me this question. I know that I have this table which has the answer, or from which I can derive the answer. Oh no, it automatically rewrites the query. So if I'm you know, doing the query at the bottom of the screen, you know, I'm asking for how many males are there in each state, or sorry, what's the top state in terms of number of males. I write my query, or my tool writes the query against the census table, but it automatically redirects it to use the census summary table. So it gets even smarter when I run a particular query. When the materialized views are created automatically. So I run a particular query where I'm interested in the number of males in particular states, and the system goes, aha, someone is interested in counting the number of males in states. I'm just going to go ahead and I'm going to build this materialization. Just in case someone has just started an interactive session, or just in case there's some VP in the organization who's really interested in this, and a lot of people are going to be asking questions about this, I'm going to go ahead and build this in the background. And so when the next query comes in, even though it may look, you know, textually it's quite different, but it's still dealing with states and genders, that second query can draw on the same materialization and can answer the result and answer the question by reading 100 rows. So this is, Asimov says, you know, sufficiently advanced technology is indistinguishable from magic. I mean, this beats brute force any day. This is definitely about working smarter. And the technology to do this is within our grasp because we have query optimization technology. So here are classic materialized views. This is kind of a primer on how Oracle or so forth does materialized views. It's a table defined by a query. It's designed by DBA, and the DBA types this create materialized view statement in. And it's stored just like a regular table on disk. You could even create indexes on it and all the other good stuff you can do with tables. The database populates the table automatically. When you execute queries, they are automatically rewritten. Now, the double asterisk is, this is where the magic happens. And this magic is, you know, stuff that I'm developing, it's under development. It's magic, but it's solvable magic. And then if the underlying data changes, so for example, if you add a new sale arrives, or you delete a product or something like that, the materialized view gets updated automatically. That also requires some magic. What I'm proposing we do in Hadoop is slightly different, but definitely building on those ideas. It's more in some ways and less in other ways. And by the way, the acronym DIMMQ, I don't even know how to pronounce it. It's an awful acronym. I just needed some handle to describe this. I don't expect this is going to be in product brochures in 2 years' time. You know, I expect that we're going to be talking about materialized views. You know, in terms of, I hope that Hive has a create materialized view statement. By the way, I hope Apache Drill has a create materialized view statement. I hope that, you know, a bunch of other Apache projects are, and commercial products are using this as well. You know, it all makes Hadoop stronger. Anyway, I hate the word DIMMQ, and you know, the marketing person who posted my blog on Hortonworks blog the other day called it DMMQ, and that term seems to be getting more resonance. I don't particularly care. What I want is the concepts. And I also think these concepts will change as we start talking about them. So one important thing is I want this to be in memory, because you remember where I started with this is I wanted to figure out how to use memory more effectively. And the way that business intelligence tools work is they operate on data in memory. They pull the working set into memory and work on it. And I want that particular use case to work really well. But they may also be on disk, just like a conventional materialized view. HDFS is part of the implementation stack to make this work, because I want these things to be shareable. And HDFS may discard them. I want them to be like a cache in that respect, in that the cache, if it's short of resources, can decide to throw them away. So this involves changes to HDFS to make it work. And Sanjay's in the front row here. He produced a proposal. Actually, the blog was posted on the same day for distributed discardable memory. So that's kind of a part of what will be necessary to make this all happen. And in terms of lifecycle support, at first I think it'll be more limited. I think we'll just assume that the table is populated. Someone has basically handwritten a Hive statement or a MapReduce job or whatever it is to populate this table. And they just say, here's a table, here's a query. Believe me, the table's populated with this stuff, go ahead and use it. Or perhaps something it gets populated as a query result set. I'm not quite sure how this will work, but I think even with limited lifecycle support, I think this will still improve an awful lot of things. And the last aspect that I think will be different is I envisage these things being created in a lot more ways than just someone writing a create materialized view statement. I want these things to be created automatically as a result of queries, query result sets, but also some agent there sitting observing query load on the system and starting to build these things. Somebody always asks, so I'm going to kind of, somebody always asks, how do these compare with Spark RDDs? Spark has been an inspiration to this because, Spark was one of the, innovative technologies that made really good use of memory when no one else was, everyone else was operating from disk. And the differences aren't really that fundamental. And I don't really want to start an either or battle. Is this against Spark? I mean, this is bringing some of the goodness that Spark brings, but bringing it to the SQL-based systems such as Hive and Pig and cascading. So think systems based more on an algebra as opposed to being a workbench based on people writing code, writing Scala code. I guess if you want to see more about these differences, the number one difference is how you access it. In these materialized views, you access them by the optimizer algebraically mapping the expression of the SQL query onto the expression that defined the view. Whereas in Spark, if you want to use an RDD, you basically need to use a variable which contains a pointer to the RDD. And that's a kind of fundamental difference. Data independence is something, it's one of the core values that, database folks are taught in their database preschool. Data independence is this idea you ought to be able to move your data around, reorganize it, and your application doesn't know, but it just gets faster automatically. And Hadoop has had kind of limited forms of data independence in that you can create different, multiple replicas, but it hasn't been as strong in terms of data independence as RDBMSs have been. And I want to change that. Materialized views are, oh my goodness. Materialized views are a powerful way of doing that, because you can basically say, here's some data over here, here's some data over here, which is equivalent to it. And so you can create the data in multiple different organizations. For example, Vertica pioneered this idea of having two different versions of the same table, different sets of columns with different sort orders. And if you want to, if you want to group by state, then you choose the table which is ordered by state, because then doing a group by state is really, really easy. If you can say I've got two copies of the same data, then you can start to do, or perhaps this is a summary of this data, or this is a subset of this data. If you can tell the system about all these multiple redundant copies that exist, oh, and yes, here's a copy of this data in memory, then a lot of things start to be possible. And they start to be possible automatically, so your BI tools or whatever your application is doesn't have to be rewritten to use it. So, kind of a sketch. This is kind of some of the work that will be required to various Hadoop ecosystem components to make this vision happen. Relational algebra, which is my main area. You need some query optimizer technology to be able to transform these expressions to recognize that this expression is the same as that. We need, changes to the cost model to recognize in-memory data versus disk-based data. We need some metadata, so probably there would be, Hive or whatever would have a create materialized view statement, and these definitions of these materialized views would go into something like hcatalog. Doesn't have to be this way. I mean, the metadata could be somewhere else, but this is kind of one of the most straightforward ways of implementing this. And then, as I mentioned, changes to HDFS. I'll explain later why discardability is so important. But clearly, we want to be able to store HDFS, to be able to store data in memory, to be able to tell HDFS, this is a table I want you to try and keep in memory, or I want you to keep it only in memory, and if you run out of memory, just throw it away. Or I want you to keep it in memory, but if you have time, then slowly page it to disk, or keep one copy in memory, 2 copies in disk, that kind of thing. The reason HDFS is part of this is I wanted these things to be incredibly shareable. I didn't want it to be one user running on this, creating all these wonderful materialized views, and the other user sitting next to them who's executing very similar queries, not getting the benefit of them. I wanted these materialized views to be global, modulo security and data freshness and all of that, and transactional context and all that stuff. But if user A has created something, user B should be able to leverage it. This is kind of a more advanced case of, let's suppose we're executing a query, select sum of column Y, group by column X. And the base table, there isn't a materialized view that covers the entire base table, but the optimizer notices that it's got a materialized view covering the first part of it, and it's got another materialized view covering the last part of it, and the stuff in the middle isn't covered, so it just goes to the base table. Well, we've saved, more than 50% of our I/O there, and we've saved, a lot of computation costs, because it's not just about reading the data; it's about munging it together, putting it in a hash table or whatever. So it's still a big win. being able to do this. And it also means we don't have to build a monolithic materialized view for the entire table. We can just create a materialized view for this year, and then someone comes along who's interested in last year, they can create a materialized view. So these things can be fairly discrete, fairly manageable sizes. And perhaps no one's interested in 2010 anymore, so that materialized view gets thrown away, but we've still got the coverage for 2014, 2013. So I see these materialized views, materialized queries as kind of coming and going in the system dynamically, and the system self-optimizing. This is, it's a grand vision, but it's something worth driving towards. So yeah, just continuing that general thought. The system should be adaptive. I don't want to have tools saying, load this data into memory. Okay, is it loaded yet? Let's start. I want the system to start bringing this stuff in, and not just old-fashioned dumb buffer cache, but smart caching. So an adaptive system, it's an optimization problem, not in the sense of query optimization, but in the sense of, the kind of thing people write PhDs on that I don't understand, but how to make optimal use of resources when there's a lot of complicated stuff going on. And the sketch of how this works is you've got an agent that's suggesting new materialized views. Materialized views are being built in background, but they aren't holding up queries that are going on. Users are saying, hey, I just updated my data. Throw that stuff out. It's giving inaccurate results. And so maybe that triggers a new materialized view being built. Meanwhile, HDFS, the agent is maybe suggesting a whole bunch of materialized views. The agent is trying to be helpful and saying, this might be useful. Go ahead and build this. This might be useful. HDFS, meanwhile, is saying, hey, I'm running out of memory. This thing you suggested 2 days ago isn't being used. I'm going to throw it away. So you've got this kind of cycle going on of the agent suggesting new stuff and HDFS basically acting as the like the restaurant critic, choosing which stuff really deserves to, or St. Peter at the gates of heaven, choosing what stuff deserves to live on and what stuff needs to be thrown out. So this kind of cycle, I believe, is an approach to get this system which is adaptive, self-optimizing, and still reasonably manageable. So hopefully we end up with this dynamic equilibrium. This is, as they say, a research topic, but this is a sketch about how one should approach this problem. I'd like to hear from you folks about whether you think I'm completely barking mad or whether this is, a good approach to take. A word about Lambda architecture. This is, another good idea that has been had, and Nathan Mars invented the term. I don't think he invented the architecture. The architecture has, well, it makes so much sense that I think it's been invented multiple times. But Nathan Mars did the work of codifying it and describing it. The basic idea is that if you've got data arriving in streams, and you've also got data arriving in real time, you've also got batch historic data, and you need to make this accessible through a query interface. He came up with this idea of creating views using batch jobs to a batch job to create a materialized view that is a summary of the historic data, and using something like Storm to compute a real-time view that's continually changing, but still a summary of what has happened over the last period of time. And then integrating those through a query interface so the end user can't really tell whether they're looking at historic data or they're looking at recent data. Now, in my view, what I'm building here is something very similar to the Lambda architecture. It's this basic idea of taking the large amounts of historic data and automatically compiling it down to a summary. And that summary is valid for a certain amount of time, and is much smaller. It's small enough to be loaded into memory. And then naturally the query interface is SQL or some kind of relational algebra interface. The good thing about this, as opposed to the kind of classic Lambda architecture, is the classic Lambda architecture requires quite a lot of, well, duct tape to, you need to write your application so that it understands how to read these results that have been generated by the batch system. In this system, it's the query optimizer which is doing the work of figuring out which is the appropriate materialized view to be looking at. Again, lots of other research topics or lots of other variations on this theme. Kind of brainstorming this with Sanjay, who's the architect of HDFS, or one of the architects of HDFS. We realized that there were kind of these three concepts: discardability, in-memory, and, well, materialization, or the algebraic, using stuff by algebraic rewrite. There are these three concepts, and they're actually orthogonal. Each of them is useful in itself. So, if you put the three together, you get these discardable in-memory materialized queries. If you kind of remove one of them or two of them, you still have something useful. So materialized queries don't have to be in memory. If they're not in memory, they're on disk. They're kind of classical database materialized views. They're still really useful. This thing, this materialized view might be 1,000th of the size or 1,000,000th of the size of the data on disk. So it's still, your queries will still run a lot faster. They don't need to be discardable. They don't need to be accessed via SQL. There are, other ways of getting into the relational algebra of the system, like PIG, cascading, and so forth. As I mentioned earlier, these things allow novel data structures to be described. So even if you're not even interested in dynamic caching, if you wanted to define, let's say, a B-tree index in Hive, Hive doesn't have a B-tree index as far as I'm aware. I think it had some form of bitmap indexes. But if you wanted to be able to describe a B-tree index, you could create a materialized view and say, here's your sales table, and here's the sales table, the sale ID and the product ID, and it's ordered by product ID. And then just tell the system, here's a materialized view. And the optimizer should be able to figure out that it's quicker to do a join to this materialized view and then onto the sales table than it is to do a full scan of the sales table. That kind of idea of a mechanism like a snapshot saying, here are two identical copies of this table, one in Tokyo and another one in Los Angeles. And if you're in Beijing, you probably want to use the one in Tokyo because it's closer. That is a very simple form of materialized view. It's create materialized view as select star from T, but it's still a materialized view, and so forth. So these ideas, I think, could create some really interesting new technology. Lastly, almost lastly, this idea, we want the system to be able to automatically create materialized views as the system is running. And that is actually asking a lot of the query optimizer. And for the classic BI use case, which is still, well, as prevalent as ever, it's very typical for the data to be arranged in a star schema, a central fact table with lots and lots of records, dimension tables describing those records like products and time periods and customers and so forth. And you know, there are mandatory many-to-one relationships, so every sale has a product ID which must correspond to a product in the product table. And just telling the system that these tables are likely to be used in this particular relationship, that data structure I would call a lattice. And if you create this data structure in HCatalog, the basic idea is that some agent will then start collecting statistics. So every time it sees a table, which is combining the sales fact table and the product table and the customer table, it goes, aha, this maps onto this lattice. First of all, I'm going to remember that someone has executed a query that could have used a materialized view. That's step one. Step two is if it sees sufficient queries that are using this, it'll say, okay, a lot of people are using, you know, customer or, you know, group by zip code. I'm going to create a materialized view for that. I'm going to throw it into memory, and I know that if it doesn't get used, HDFS is going to throw it out. So this lattice is really a piece of metadata which acts as a hint to the system. You don't write queries against this. You don't reference sales star in a query, but it's a piece of metadata that gives the system a very strong hint that it should start looking for opportunities to create materialized views. So to sum up, I always feel like this is a circus metaphor with, you know, elephants under the tent. But Hadoop is, one of the great things about Hadoop is it's a very broad tent. It's a place to put all of your data and operate on it using different engines, and the data can be in different formats and so forth. And this broadens the tent to not just traditional batch data, but to new forms of, you know, new access patterns for data. And, you know, interactive BI is one of my motivating ones, but streaming and iterative can also be done using this. And it allows it to be transparent, which means all of these people that are using Hadoop via tools, the tools don't need to change, the end users don't need to change their applications, but it just gets faster. The application automatically uses memory. And this means you have to have seamless movement between memory and disk. You can't just say, oh, load all this data into memory and it'll just run faster. Yeah, adding brains to Hadoop is my mission here. So I think we have probably about 2 minutes left. Are any quick questions? Yes.
So you said the materialized views are stored in a disk format. Is it something like what's the source data format is, like Parquet, or what's the simulation format?
Yeah, the question was the materialized views are stored in disk format. What is that format? The idea is they're stored basically in the same format you'd store tables. You know, ORC file, something like that. And you know, those formats, perhaps we'll start evolving those formats so they work slightly better for in-memory. But I don't really want to invent a new format for these. I want them to work the same as on disk. I guess one more question. Yes?
So you only say it's going to support high mobile team. Will the team be putting things?
Yeah, I didn't say that. We definitely intend to roll it, to make this available to everything. You know, since I'm talking about SQL and SQL's how we reason about this, I'm naturally talking about Hive first. But yeah, we definitely want to make it available through multiple. We want to make it accessible to multiple engines, not just SQL-based ones. Okay, thank you very much.